Dear students, welcome back to the final session of this chapter, Current Electricity. As usual, more care to be taken as and when you see a circuit diagram or an illustration, follow the diagram and listen to my explanation only. Let's move on to the session. Electromotive force of a cell. The electric cell maintains a constant difference in potential between the two conductors by a chemical reaction to obtain a continuous flow of charge between them. Thus, a cell stores the chemical energy and it can be used as a source of current. The chemical energy changes into the electrical energy when the cell is in use. The figure shows an electric cell having two electrodes, one of zinc and other of copper, placed in an electrolyte like dilute sulfuric acid. The electrolyte in water dissociates into positive H plus ions and negative sulfate ions. These ions move towards the electrodes. The negative ions impart electrons to the zinc electrode and positive ions gain electrons from the copper electrode. This chemical action creates a difference in concentration of electrons between the two electrodes of a cell. As a result, the zinc electrode acquires a negative potential called the cathode, and the copper electrode acquires a positive potential called the anode. That is, a potential difference called the electromotive force, in short EMF, is created between the two electrodes of the cell. When no current is drawn from a cell, that is, when the cell is in open circuit, the potential difference between the terminals of the cell is called its electromotive force or EMF. The EMF of a cell is generally denoted by the symbol epsilon. Its unit is volt. It can be measured by connecting a voltmeter of high resistance across the cell. When some electrical component such as bulb etc. is joined to the terminals of the cell, electrons flow in the external circuit from the zinc electrode to the copper electrode, or current flows in the external circuit from the copper electrode to the zinc electrode. The current flows in the external circuit because the EMF between the terminals provide energy for the charge to flow through the component joined in the circuit. Now, what are the factors affecting the EMF of a cell? The EMF of a cell is defined as the energy spent or the work done per unit charge in taking a positive test charge around the complete circuit of the cell. That is, in the circuit outside the cell as well as in the electrolyte inside the cell. If capital W work is done in taking the test charge Q around the complete circuit of the cell, then EMF of the cell is epsilon is W by Q. Consider this as equation 1. The factors that affect the EMF of a cell are: it depends on the material of the electrodes, and 2, the electrolyte used in the cell. However, it is independent of the shape of electrodes, the distance between the electrodes, and the amount of electrolyte in the cell. Thus, the EMF of a cell is its characteristic property. It is different for different kinds of cells. For example, the EMF of a voltaic cell is 1.08 volt and that of a Lagrange cell is 1.5 volt and of a Daniell cell is 1.08 volt. Now, what is terminal voltage of a cell? When current is drawn from a cell, that is, when the cell is in closed circuit, the potential difference between the electrodes of the cell is known as its terminal voltage. The terminal voltage of a cell is generally denoted by the letter capital V. It is also expressed in volt. The terminal voltage of a cell is defined as the work done per unit charge in carrying a positive test charge around the circuit connected across the terminals of cell. If W is the work done in carrying a test charge Q around the circuit connected across the terminals of the cell, that is, only outside the cell and not inside the cell, then the terminal voltage of the cell is capital V is W prime by Q. Consider this as equation 2. From the definitions of EMF and terminal voltage of a cell, it is clear that the terminal voltage V of a cell is less than its EMF epsilon by the amount of energy spent in the flow of charge through the electrolyte inside the cell. If W is the work done in carrying a test charge Q through the electrolyte inside the cell, then the quantity W by Q is called the voltage drop in the cell, which is denoted as V. That is, voltage drop in the cell V is equal to W by Q. Consider this as equation 3. Thus, the work done per unit charge in carrying the positive test charge through the electrolyte is called the voltage drop in the cell. It is so called because this voltage is not available to us for use. Relationship between EMF and terminal voltage of the cell. If W is the work done in moving the test charge Q outside as well as inside the cell, W prime is the work done in moving the test charge Q outside the cell, and small w is the work done in moving the test charge inside the electrolyte of the cell, then by the law of conservation of energy, capital W is equal to W prime plus small w. Consider this as equation 4. Dividing the above equation by Q on both sides, we get W by Q is equal to W prime by Q plus small w by Q. Consider this as equation 5. But from equations 1, 2 and 3, W by Q is epsilon, W prime by Q is capital V, and small w by Q is small v. Therefore, from equation 5, epsilon is equal to capital V plus small v, or capital V is equal to epsilon minus small v. Consider this as equation 6. Thus, when current is drawn from a cell, its terminal voltage V is less than its EMF by an amount equal to the voltage drop small v inside the cell. When a heavy current is drawn from the cell, a large number of charge carriers flow through the electrolyte and hence more work is done. This results in more voltage drop V and hence less terminal voltage capital V. Thus, the terminal voltage V of a cell depends on the amount of current I drawn from it. The internal resistance of a cell. The resistance offered by the electrolyte inside the cell to the flow of current is called the internal resistance of a cell. It is the internal resistance of cell due to which its voltage drops on drawing current from it. It is denoted by the symbol small r. Its unit is ohm. When current I is drawn from the cell of which internal resistance is R, then the voltage drop V is equal to IR. Consider this as equation 7. Now, let a cell of EMF epsilon and internal resistance small r be used to send current in an external resistance capital R connected across the cell as shown in the figure. The total resistance of circuit is R plus R. Consider this as equation 8. The current now drawn from the cell is I is equal to the EMF of cell divided by total resistance, which is epsilon by R plus R. Consider this as equation 9. The EMF of cell is equal to EMF of cell epsilon is equal to I into R plus R. Consider this as equation 10. The terminal voltage of the cell is then V is equal to IR, which is equation 11, and voltage drop due to internal resistance is small v is IR, which is equation 12. From equation 9, 10, 11, epsilon is capital V plus small v, or V is equal to epsilon minus capital V. Then from equations 11 and 12, the internal resistance R is small v by I, which can be written as epsilon divided by V minus 1 into R. Consider this as equation 13. Now, what are the factors that affect the internal resistance of the cell? 1. The surface area of the electrodes. Larger the surface area of electrodes, less is the internal resistance. The distance between the electrodes. More the distance between the electrodes, greater is the internal resistance. The nature and concentration of the electrolyte. Less ion the electrolyte, or higher the concentration of electrolyte, greater is the internal resistance. And finally, the temperature of the electrolyte. Higher the temperature of electrolyte, less is the internal resistance. Now let's move on to see the combination of resistors. Resistors can be combined in three ways. 1. In series, 2. In parallel, and 3. Both in series and parallel. Let's see the combination of resistors in series. Look at the diagram. In the series combination, the resistors are joined one after the other. In figure, three resistors R1, R2 and R3 are connected in series between the points A and D, such that one end of resistor R1 is connected to the point A and its other end to the resistor R2. The other end of resistor R2 is connected to one end of resistor R3 and the other end of the resistor R3 to the point D. The end A and D of the combination are then connected to the terminals of a battery through a key capital K. The following two facts can be noted about the series combination. Students, what is highlighted, you should remember them. The current has a single path for its flow. Hence, in series connection, same current passes through each resistor. Remember this point. So, the potential difference across any resistor is directly proportional to its resistance. Thus, the potential difference is different across the different resistances. So, current is same, but potential difference is different. The potential difference across the entire circuit is equal to the sum of the potential difference across the individual resistors. That is, V is equal to V1 plus V2 plus V3, so on. Now, what is the expression for the equivalent resistance? If current I is drawn from the battery, the current through each resistor will also be I. By Ohm's law, potential difference between A and B is V1 is equal to IR1. Potential difference between B and C, V2 is IR2. Potential difference between C and D is V3, which is IR3. Adding these, we get V is equal to V1 plus V2 plus V3, which is equal to I into I taken in common R1 plus R2 plus R3. Consider this as equation A. If the equivalent resistance between the points A and D is Rs, then the potential difference between the points A and D is V is equal to I into Rs. Consider this as equation B. From equations A and B, IRs is equal to I into R1 plus R2 plus R3. Cancelling I on either side, Rs is equal to R1 plus R2 plus R3. Thus, in the series combination, the equivalent resistance is equal to the sum of the individual resistance. In general, if n resistances joined in series are R1, R2 till Rn, then the equivalent resistance is given as Rs is equal to R1 plus R2 plus Rn. if there are n equal resistances, each of value R, connected in series, the equivalent resistance Rn is equal to R plus R till n time, which is n into R. Let's see an example. If we connect three resistors of resistance 2 ohm, 3 ohm and 5 ohm in series, the equivalent resistance Rs of the combination is Rs is equal to R1 plus R2 plus R3, which is 2 plus 3 plus 5, 10 ohms. Now let's see the combination of resistors in parallel. Look at the circuit diagram. In the parallel combination, one end of each resistor is connected at one point A and the other end of each resistor is connected together at the other point B. The battery along with the key is then connected in between the points A and B as shown. If the circuit is closed, the current I drawn from the battery divides itself at the point A in three parts: I1 in resistance R1, I2 in resistor R2, and I3 in resistor R3. The current in a resistor is inversely proportional to its resistance. Less the resistance, more is this current in it. The potential difference across the resistor is same. Students, please make a note. Here in parallel connection, the potential difference is same but current is different, which is equal to the potential difference across the terminals of the battery. The current in a resistor is inversely proportional to its resistance. The sum of currents I1, I2, I3 in the separate branches of the parallel circuit is equal to the total current I drawn from the source. That is, I is equal to I1 plus I2 plus I3. Let I1, I2 and I3 be the current through the resistance R1, R2 and R3 respectively. Look at the diagram. Then the total current drawn from the battery is I is equal to I1 plus I2 plus I3. Consider this as equation A. If the potential difference between the two ends A and B is capital V, then by Ohm's law, current in R1 is I1 is equal to V by R1, current in R2 is I2 is equal to V by R2, and current in R3 is I3 is equal to V by R3. On adding these I1 plus I2 plus I3, we get V by R1 plus V by R2 plus V by R3, which is equation B. If the equivalent resistance of the combination between the points A and B is Rp, P standing for parallel connection, then total current drawn from the source is I is equal to V by Rp. Consider this as equation C. Substituting the value of I and I1 plus I2 plus I3 from equations B and C in equation A, we get V by Rp is equal to, taking V out in common, V into 1 by R1 plus 1 by R2 plus 1 by R3, or 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Consider this as equation D. Thus, in parallel combination, the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistances. In general, if n resistance, that is R1 till Rn, be joined in parallel, then the equivalent resistance Rp is given as 1 by Rp is 1 by R1 plus 1 by R2 till 1 by Rn. Consider this as equation E. If there are n equal resistances, each of value R, connected in parallel, the equivalent resistance Rp is given as 1 by Rp is equal to 1 by R plus 1 by R till n terms, which is equal to n by R, or Rp is equal to R by n. Consider this as equation F. For two resistances R1 and R2 connected in parallel, the equivalent resistance Rp is given as 1 by Rp is 1 by R1 plus 1 by R2, which can be written as 1 by Rp is R2 plus R1 divided by R1 R2, or the resistance, equivalent resistance in parallel for this condition is R1 R2 divided by R1 plus R2. Now let's see the combination of resistors both in series and parallel. Students, sometimes to obtain a desired value of resistance from the given resistors, we connect some resistors in parallel, and this parallel combination of resistors is connected in series with some more resistors as shown in the diagram. A branch of parallel combination may also have two or more resistors in series combination. Similarly, there can be more than one parallel combination in series also. In such a case, we first determine the resistance of each branch of parallel combination. Then we determine the equivalent resistance of each parallel combination. After this, we find the total resistance by adding each resistance and the equivalent resistance of each parallel combination connected in series. With an example, you will understand. Look at the diagram. To obtain an equivalent resistance of 1.5 ohm using three resistors of 1 ohm each, we connect a parallel combination of two resistors in series with a third resistor as shown. In figure, the equivalent resistance of parallel combination is Rp is, since they are 1 ohm each, R1 into R1 R2 divided by R1 plus R2, that is 1 into 1 divided by 1 plus 1, which is 0.5 ohm. Now the total resistance in series will be R is equal to R1 plus R2, that is the effective resistance 0.5 plus 1 ohm, which is 1.5 ohms. Let's see some special conditions. Look at the first diagram. For the two resistors joined in series, the equivalent resistance is more than they are joined in parallel. Therefore, on IV graph, that is current voltage graph, the straight line obtained will have less slope than that for a parallel combination as shown in figure, because resistance is 1 by slope on IV graph. In figure, the straight line A corresponds to the parallel combination of resistors, while the straight line B corresponds to the series combination of resistors. Second case, if current I is divided into two resistances R1 and R2, which are connected in parallel as shown, then I is equal to I1 plus I2 and I1 R1 is equal to I2 R2. Hence, the current in the resistance R1 is given by the formula I1 is equal to IR2 by R1 plus R2, and current in resistance R2 is I2 is equal to IR1 by R1 plus R2. The third case, if voltage V is divided into two resistances R1 and R2 connected in series as shown, then current drawn from the cell I is equal to V by R1 plus R2. The potential difference across R1 is V1 is equal to IR1, which is VR1 by R1 plus R2, and potential difference across R2 is V2 is equal to IR2, which is V into R2 divided by R1 plus R2. The measurement of electrical energy, which gives the expression W is equal to QV or W is equal to VIT. In figure, let a current I be flowing through a conductor of resistance R for time t, when a source of potential difference V is connected across its end. Due to flow of current I for a time t, the amount of charge passing is Q is equal to I into T, because by definition I is rate of flow of charge. By definition of potential difference, work needed to move a charge Q through a potential difference V is W is equal to Q into V. But we know Q is equal to IT. Therefore, replacing Q, we have W is equal to V into I into T. Thus, equation 2 gives the electrical energy W supplied by the source in providing the current I for a time period of t seconds in the conductor under a potential difference V. The other expressions for electrical energy by the use of Ohm's law. By Ohm's law, we know V is equal to IR. Therefore, from equation 2, W is equal to I squared RT, and also W is equal to V by R the whole squared into RT, which is V squared T by R. Thus, electrical energy supplied by the source W is equal to QV can be written as VIT, which is also equal to I squared RT, which is also equal to V squared T by R. The SI unit of electrical energy is joule. In an electrical circuit, electric power is defined as the rate at which the electrical energy is supplied by the source. If a source of potential difference V sends a current I for a time period T in a resistance R, the charge passed is Q is equal to I into T, and the energy supplied by the source is W is equal to QV. Then power is energy supplied W divided by time T, which is equal to QV by T. Since Q is equal to IT, P becomes VIT by T or VI. By Ohm's law, we know I is equal to V by R. Therefore, P is equal to V squared by R. Since V is equal to IR, P is equal to IR the whole square divided by R, which is equal to I squared R. Thus, electrical power can be written as work by time, which is equal to voltage into current, which is also equal to V squared by R and also equal to I squared R. These formulae are very much useful for us to solve numerical problems. The unit of electrical power. The SI unit of potential difference is volt, of current is ampere. So the SI unit of electrical power is volt into ampere or watt or joule per second. In relation P is equal to V into I, if V is equal to 1 volt and I is equal to 1 ampere, then power is 1 watt. Thus, definition of 1 watt is the electrical power consumed when a current of 1 ampere flows through a circuit having a potential difference of 1 volt. Bigger units of electrical power are kilowatt, which is 10 power 3 watt, megawatt, which is 10 power 6 watt, and gigawatt, which is 10 power 9 watt. Commercial unit of electrical energy. The SI unit of energy is joule. If an electrical appliance of power P watt is used for time T second, the electrical energy consumed is W is equal to power into time. W is equal to P into T. In practice, the electrical energy is measured in bigger units, watt into hour and kilowatt hour. Let us define 1 watt hour. It is the electrical energy consumed by an electrical appliance of power 1 watt when it is used for 1 hour. Thus, 1 watt hour is equal to 3600 joule. Now, what is 1 kilowatt hour? It is the electrical energy consumed by an electrical appliance of power 1 kilowatt when it is used for 1 hour. Thus, 1 kilowatt hour is equal to 3.6 into 10 power 6 joule. Power rating of common electrical appliances. Students, generally an electrical appliance such as an electric bulb, geyser, heater, etc. is rated with its power and voltage. For example, an electric bulb is rated as 100 watt and 220 volt. It means that if the bulb is lighted on a 220 volt supply, the electrical power consumed by it is 100 watt. That is 100 joule of electrical energy is consumed by the bulb in 1 second. From the rating of an appliance, we can calculate the following two quantities. 1. The resistance of its filament or element when it is in use, and the safe limit of current which can flow through the appliance when in use. From relation 6, P is equal to V squared by R, resistance of element of the appliance while in use is R is equal to V squared by P. That is, R is voltage rating of the appliance the whole square divided by power rating on the appliance. And the current through the element of appliance when in use is I is equal to P by V. If current exceeds this value, the power supply at voltage V will exceed the rated power of the appliance and the appliance may get damaged. So this value of current is called the safe current, which can flow through the appliance at voltage V. Thus, safe current I is power rating on the appliance divided by voltage rating on the appliance. Let's see the power rating of common electrical appliances with an example. If the bulb is rated 100 watt and 220 volt, the resistance of its filament while glowing is R is equal to V squared by P, which is 220 squared by 100, which is 484 ohm. The safe limit of current through the filament of bulb while glowing is I is equal to P by V, which is 100 divided by 220, is 0.45 ampere, which can be taken as 0.5 ampere. Thus, the bulb can withstand a current of 0.5 ampere. If current exceeds 0.5 ampere, it may cause the bulb to fuse. At a voltage higher than the rated value, an excessive current will flow through the filament of the bulb, which will raise its temperature to an extent that the filament will melt and the bulb will get fused. If a bulb is rated 100 watt and 220 volt, it consumes 100 watt power at 220 volts, and the resistance of its filament while glowing is 220 the whole square divided by 100, which is 484 ohm. Now, if this bulb is lighted at 110 volt, it will consume power equal to 110 the whole square divided by 484 watt, which is equal to 25 watt. But if the same bulb is lighted at 250 volt, it will consume power equal to 250 whole squared divided by 484 watt, which is 129.1 watt. Let's see the household consumption of electrical energy. The electrical energy consumed by an appliance in a certain time can be calculated in kilowatt hour by the following relation. Energy is power into time. Now, power in watt into time in hour divided by 1000, which is power can be replaced by voltage and current into the time divided by 1000. From relation 8, it is clear that the total energy consumed by electrical appliances in kilowatt hour can be calculated by multiplying its power rating in kilowatt with the time duration in hour for which it was in use. The cost of electricity will then be the product of energy consumed in kilowatt hour with a rate in rupees per kilowatt hour. The cost of electricity is electrical energy into cost per kilowatt hour. Let's see an example. If an electric oven of power 3 kilowatt is used for 2 hours each day, the electrical energy consumed by the electric oven per day will be 3 kilowatt into 2 hour, which is 6 kilowatt hour, while the total electric energy consumed in a month of 30 days will be 3 kilowatt into 30 into 2 hours, which is 180 kilowatt hour. The cost of electricity at a rate of 4.5 rupees per kilowatt hour will then be 180 into 4.5, which is rupees 810. Finally, the heating effect of current. The amount of heat produced in a wire on passing current through it depends on the following three factors. 1. The amount of current passing through the wire. The amount of heat produced in a wire is directly proportional to the square of current I passing through the wire. H is proportional to I squared. The resistance of wire. The amount of heat produced in the wire is directly proportional to the resistance R of the wire. H is proportional to R. The time for which current is passed in the wire. The amount of heat H produced in a wire is directly proportional to the time T from which the current is passed in the wire. H is proportional to T. Combining all these equations, H is proportional to I squared RT, or H is equal to I squared RT joule. H can be written as 0.24 I squared RT calorie, where I is in ampere, R in ohm, and T in second. The relation D is also known as the Joule's law of heating. Students, that brings us to the end of the session and the chapter as well. Please go through the presentation as many times for a better understanding. Bye till we meet again.